Hello, calculus students and general seekers of truth, and this is the point where we get to the general truths here. So the goals, we estimated this function, done. Now we're going to work on 2, and we're going to try to find the exact area of this function. So if you recall from what we did earlier, we just diced up this into a bunch of little rectangles and found these points in a very special way. Now we're going to expand and extend on this concept. Okay. And we're going to apply this mantra, and that's often said in calculus, is that if you want more accuracy, well, you just use more rectangles, but smaller rectangles. In other words, in the last example, we did this with 4 rectangles. Now we need to just do this with, we want to get more accuracy. Well, we're going to get smaller rectangles and get more of them out of there. And so that begs the question, what if you want perfect accuracy? And we can extend on that. Well, if you want perfect accuracy, then we want infinitesimally small. This is an actual word. I looked it up. It means as small as you can get without reaching 0. And infinitely many. In other words, dice up that picture into very, very tiny rectangles, but not 0. As small as you can go to, but not 0. And make sure you create an infinite number of them. Okay? And in the calculus, of course, the way we deal with this is the limit. Okay? So I've written it out here. This definite integral is exactly equal to the limit as n approaches infinity of this right here. Remember from previous lessons, this is the width of each rectangle. This expression here, this whole thing, is the height of each rectangle. Okay. That's the height of each rectangle. Now we're going to rewrite a few things, and at this point, once again, it's important for you to understand how this works. I'll explain why it works at the end of all of this. So we are going to rewrite a few things here. We are going to say that instead of n going towards infinity, we're going to say the limit as delta x approaches 0. Okay. So instead of n being the number of rectangles going towards infinity, we're going to take the limit as delta x approaches 0, where delta x is the width of each rectangle. Okay, and if you look at the picture and how we do this, it's basically the same idea. Instead of taking the limit as having many rectangles, we're going to take the limit as each one of these rectangles get really, really small. Okay, so using this same idea up here, infinitesimally small, infinitely many rectangles. So we can, here we have the limit as the number of rectangles goes towards infinity. We're going to change this limit as the width of each rectangle go down to 0. The reason we're doing that is we want to avoid infinity here. Having infinity here for the case of the cosine function actually leads us to some problems. Okay? And then instead of writing this out as pi over 2 minus 0 over n, I'm actually going to bring this inside the function. So this is cosine of c sub I times pi over 2 minus 0 over n. Okay, so this I know seems very, very weird. And then I'm actually going to make it even more counterintuitive than that for the moment. So this thing here, I'm going to rewrite this as x sub I minus x sub I minus 1. Okay, so let me explain what this red part really means. And I'll show you why this section means the exact same thing as this section. Okay, so if you look back into this picture, x sub 1 is pi over 8, x sub 0 is 0, so if you subtract those two, you get pi over 8. X sub 2 is pi over 4, x sub 1 is pi over 8. If you subtract these two, you still get pi over 8. And if you do this for each of the intervals, you're still going to get pi over 8. But I'm going to write it out this way instead, because you'll see in a minute that it's going to be much more useful to us this way. Okay. So, for example, x sub I, let's say I is 1, so that means x1 minus x0, since x sub I minus 1 is x0. Okay. Now, on to probably the trickiest and perhaps most challenging part of all of this. So I'm going to rewrite this limit. So we've written everything the same except for cosine of c sub I. Cosine of c sub I is exactly equal to sine of ci minus sine of c1. I'm sorry, sine of ci minus sine of ci minus 1. Okay. In other words, if you look at what we did up here, let's look at this equation. Right? We try to find c sub 1, and the way we did that from before, we did sine of pi over 8 minus sine of 0, then divided by pi over 8. Right? And then to find c1 or c sub 1, what did we do? Well, we had to do cosine inverse of that, and that gave us 0.226. However, what happened? What did we do with this 0.226? Well, 0.226 is the x value here that we used to plug into the cosine function. So what we did after that was we took 0.226 and we plugged it right back into the cosine function. See? So all we did was we took the 0.226 and plugged it right back into the cosine function. So what that tells us is that rather than doing cosine of 0.226, what we could have just done was replace this thing with sine of pi over 8 minus sine of 0 divided by pi over 8 minus 0. Right? Rather than using this equation to figure out 0.226, only to plug it back into the cosine function again, we could have just skipped this step and just wrote this expression here. Sine of pi over 8 minus sine of 0 over that difference. Same thing with C2. Rather than doing this process to figure out 0.599 and then plugging it back into the cosine function, we could have just as easily done sine of pi over 4 minus sine of pi over 8, all divided by pi over 4 minus pi over 8. Okay? And we could have done the same thing with this number and this number. So leaping forward to the general case, rather than doing cosine of c sub I, we could just as easily say sine of x sub I minus sine of xi minus 1. All of this over xi minus xi minus 1. Okay. This right here is the average rate of change of the sine function between these two intervals, between these 2 points, and it happens to equal the same thing as the cosine of that c value that we were looking for. Okay. Now, I can explain a little bit more why I made this change up here from this expression to this expression. Because if you see what we have, the replacement that we have now, what we could do is we could just simply cancel this out and cancel this out, since they're the exact same thing. Now let's think about now I can also explain why I changed this limit here. Because I don't want an infinity here in n. Having an infinity here in n actually causes me some problems. It's much easier for me to take the limit as delta x goes down to 0. So then we can say that the limit as delta x approaches 0. Now let's expand this out using summation notation here and just expand it and see what this really tells us. So this means the first term that we have is sine of x1 minus sine of x sub 0. Okay? That's the first term that we have, plus the second term that we have, so I is now 2 sine of x2 minus sine of x sub I minus 1, so x1. The third term that we have is going to be sine of x3 minus sine of x2. And we're going to keep on going. We're going to keep on adding, dot, 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 until we get to the last terms, which is sine of xn minus sine of xn minus 1. And I don't know if you notice as we do this, you can see here that we have a negative sine of x sub 0. Okay. That term is somewhat unique, and we have sine of xn. Okay. This term is somewhat unique. It's unique because if you look at all the other terms, we have a positive sine of x1 and a negative sine of x1. So that cancels. Then we have sine of x2 positive and negative sine of x2 positive or negative. So these are going to cancel. So when you expand this out, everything is going to cancel. This sine of x3 right here, there's going to be a sine of x4 minus sine of x3. So every single thing is going to cancel. And the only thing that's left, so I should say that this term right here will also get canceled. This will also get canceled by the term that comes before that. And the only terms that are left, okay, are these two terms. And this is a beautiful thing, because now delta x has absolutely no influence over this at all. We can absolutely just get rid of delta x. And now we end up with sine of xn minus sine of x sub 0. Now let's think about what these numbers mean. Remember that sine of x0 is the left bound, and sine of xn is the far bound. So this comes out to just being sine of the far bound here, or the upper bound here, is pi over 2, minus the lower bound here, which is 0, or sine of 0. And what we have is sine of pi over 2 is 1, minus sine of 0 is 0. So our final answer here is 1. So I hope you see in this that the things that we do here along the way are done very deliberately. They're not done, these numbers that we chose before, they're not done willy-nilly. The reason that we choose these numbers and we choose the sine function here, okay, the reason we choose the sine function is because the derivative of sine is cosine. Okay? In other words, we want to choose a function such that when you set up this problem with the mean value theorem, the expression of the average rate of change equals exactly the value of the function you're looking for. Okay. So that when we get to this problem here with this cosine c sub I, we're able to eliminate cosine c sub I altogether, and we get sine of x sub I minus sine of x sub I minus 1 over this difference, which cancels out the width of each rectangle. And then when we expand this series here, we expand it out this way, everything in here cancels except for this term and this term. And it reduces down beautifully to a perfect number. Okay. Okay. So just to show you that this is true, I mean, we could certainly do this on a calculator as well. So we can do, not that the calculator actually behaves according to what we tell it to do, not the other way around, but it's always nice to see that our technology behaves according to our theory. So we can calculate the integral from 0 to pi over 2, and it is exactly equal to 1. Okay. So I'm going to end this video here, let you digest these ideas a little bit, and I'm going to continue one more video in this section and talk about the general idea.